Count 3 seconds. Your body just produced about 7.2 million red blood cells. According to Brookhaven National Laboratory, 4.5 million Americans would die each year without life-saving blood transfusions, making blood the most vital component in the human body. That being said, our experiment focuses on this critical issue affecting the lives of numerous individuals. First off, we would like to begin by introducing ourselves. My name is Nadia Machado. I'm a graduate from the Health Occupations Program.
My name is Jennifer Arujo, and I'm also a graduate from the Health Occupations field.
My name is Tiffany Nugent, and I'm also a graduate from the Health Occupations Program.
My name is Ryan Swift, and I'm a graduate from the Machine Technology Program.
This science experiment was open up to 1,400 Montech students, and we consider this a great opportunity for us to represent Montech and Mission 2.
Now for our proposed question, will microgravity have a significant effect on packed synthetic hemoglobin-based oxygen carriers, or HBOCs? Now before we go into our hypothesis, we need to understand some background knowledge, which is the difference between red blood cells and HBOCs. Red blood cells are cells that carry oxygen and bind hemoglobin, while HBOCs are synthetic red blood cells. Now, we chose for this project to use the HBOCs because since they are synthetic, they're more sterile. They're also a lot more efficient because they don't have any blood transfusion diseases, and they have a larger lifespan of at least 2 years. And they're also able to be stored at room temperature, unlike red blood cells. Now, our hypothesis. The hemoglobin-based oxygen carriers will not be significantly affected by microgravity conditions. When we thought about this hypothesis and the experiment, we were thinking of the idea, what if an individual in space were to have an emergency in which blood loss was a huge factor? Would we be able to store HBOCs up in space and be able to transfer them into an individual?
Due to the specific nature of our experiment, we only needed one major material to make it happen, and that is the HBOCs themselves, provided by OPK Biotech in Cambridge, Massachusetts. When we were packaging them, they were packaged in a Type 2 FME under sterile conditions in a nitrogen-rich environment to prevent the hemoglobin from activating before the experiment was started. And our results of the experiment.
The radiometer measures the electrolytes and the oximetry. Electrolytes are important because they affect the major body functions, and the oximetry, the normal range for oximetry levels range between 12.1 and 7.2 grams per deciliter. And as you can see, in the control sample, the oximetry level is 12.4 grams per deciliter, and in the space sample, it is 12.2 grams per deciliter, which proves that there is not a statistically significant difference.
Now, for an oxygen equilibrium curve, or the P50, this test measures the ion coordination and oxygen binding site in heme groups. So for our control, we have on the y-axis the percent oxyhemoglobin, while on our x-axis we have the PO2, or partial pressure of oxygen. We can see the curve, and we can also see that at percent oxyhemoglobin of 50, on our control, there's a 39 PO2. And on our space sample, there's a percent hemoglobin of 50 and a PO2 of 39. These two numbers are very similar, and they're not significantly different because of the percent error of the machine.
When hemoglobin starts binding, the pressure of oxygen is at a low level, indicating a weak binding stage and a slope greater than 1. Then as the lines approach one another, this shows a strong binding stage, which is also a positive cooperativity. A cooperativity is the binding of oxygen to hemoglobin. And as you can see on our control sample, there is a slope of 1.54, and on the space sample, there is a slope of 1.55. This shows similar results when it comes to degrees of cooperativity.
We also performed a molecular weight chromatography, which is essentially just a molecule counter. The outside of each HBOC is made up of very complex proteins that allow the oxygen to pass through the membrane, and we wanted to make sure that these did not degrade at all while they were up in space. Our control sample was identical to what the manufacturer specifies as a quality product. And then the sample that had gone up into microgravity matches our control sample exactly after it had come back to prove that there was no degradation in the samples.
And to tie up this presentation, we can say that there are no significant changes in microgravity. And for future studies, we can repeat the current test to find the definite conclusion, and we can also repeat the test analysis, microgravity, and test for Hemopure, which is a blood synthetic for animal use.
Okay, we would like to extend a special thank you to the Montachusett Regional Vocational Technical School District, to the Massachusetts Space Grant Consortium, to NIPRO and NIPRO Mold, to the North Central Massachusetts Workforce Investment Board, to OPK Biotech, especially Dr. Light, who is our facilitator for this project, and from Micron Integrated Technologies. Any questions?
While we're waiting for questions, just a little personal commentary here. I led the Step 2 review subpanel that had this experiment. We looked at Fitchburg, and we were very impressed with this experiment for two reasons. The first is whether or not synthetic blood degrades in space is really, really important for long-duration space flight in case of a medical emergency. And the second point, so from the standpoint of a powerful microgravity experiment, this was superb. The second was how elegant this experiment is in terms of simply using an FME type 1, no mixing in space. You're just sending the synthetic blood up, you're bringing it down, you're doing a point comparison to the ground truth, and now you've got real data. We'll make sure that NASA gets that information. So I'm going to turn this over for questions.
My name's Craig Hyde from East Lyme. I'm a little curious about the background of synthetic blood. So do you happen to know what the rejection rates are of synthetic blood, if there's ever been a case, especially in humans, of any issues with that?
Right now, the synthetic blood is only being used in humans in countries such as Russia and Australia and South Africa. It has not been approved for use in the US as of yet, but there's almost no rejection rate because there's no need for cross-matching or blood typing. So it's universal. It'll go to any person in here, regardless of blood type or country of origin. There's absolutely no problem with that. So there's virtually no rejection rate because it's a very pure blood sample going into you.
Great, thank you.
My name is Robert Edmiston from Brevard County, Florida. I was wondering, you said that it lasts for 2 years. I was wondering how long, if you knew how long it would last in space, or if it would stay at the 2-year.
The only way to find out is to actually send it up there for more than that amount of time. For the time that it was up in space, nothing changed at all. So it's reasonable to believe that it's going to last the same, if not longer, in space than it does here on Earth.
Okay, thank you.
Okay, let's thank Team 2 from Fitchburg, Massachusetts.